Okay, let's go now from the shallow water equation system we derived, and which basically means it's homogeneous in the vertical, so we didn't have vertical structure, and we derived the horizontal structure of the waves. We can now move to a real atmosphere but still keep the system linear but give it vertical structure, stratification, representation, so that we can look at the vertical structure of the waves as well, which is very critical because we are looking at heat source, which is going to alter the vertical structure stability, and the waves are going to propagate upward and downward, and the heat source is actually moving as well. So we are still kind of going to look for answers of how the convectively coupled equatorial waves are moving slower than free waves, and the vertical structure of the convectively coupled equatorial waves, and the parameter that we use to go from the model to the observations was called the equivalent depth. So these are a few tricky issues that has to be still resolved. So you start with the familiar zonal and meridional momentum equations, which are linearized around a background state that is still stationary. And now we have the vertical structure, so we have the continuity equation with the vertical term shown here. And here z is not the z coordinate in the Cartesian system, it's a pressure coordinate, basically because atmosphere is a compressible fluid, and we want to keep density out of the variable density out of the system to make the equation simpler. Plus, density is in general an inconvenient variable. You cannot measure it like pressure and temperature. So you convert that to rho 0 by using the pressure coordinate, and you have the vertical acceleration of the potential height, geopotential height, related to the vertical motion and vertical stability parameter, the Brunt-Väisälä frequency. So z here is defined as minus h log p over ps, where ps is the surface pressure and p is the in situ pressure. H is the scale height, which is the RTM over G, the mean temperature, and scale height is essentially the height over which any particular variable drops by one exponential. So you should get familiar with these concepts, because this is not a course we are going to get into those kinds of details. But you can begin to imagine that the vertical heating is the key driver perturbation of vertical motions, so we need to connect those. But to start with, we can combine the equation 9 and 10 into this form by introducing a linear operator, and then the equivalent depth becomes a function of the eigen values of the operator L, which is our vertical structure function. Okay, so equivalent depth then looks like n squared over g lambda, and you can assume n to be constant for simplicity to start with. So still looking for wave solutions. So you can see the relation with horizontal divergence and vertical acceleration. Horizontal convergence and divergence are going to give you vertical motion, and the divergence and convergence obviously is related to the heating as well. So we have to relate each of those things. The vertical wave parameter 2 pi over Lz. Lz is the wavelength in the vertical. Obviously, the wave number is related now to n squared and equivalent depth and the scale height. With this relation, you can plot, you can compute these numbers by to look at the vertical structure values for dry waves in a constant n atmosphere. So we haven't considered moisture here, but it shows that when you are considering a heat source and a moving heat source with certain vertical wave numbers, and you want to match the equivalent depth to the observed vertical wave lengths. For the troposphere, here you have the equivalent depth of 7.3 kilometers with a given lapse rate of -7 Kelvin per kilometer, and here are the different equivalent depths corresponding to the wavelengths in the vertical, and that's the gravity wave speed, and that's the Rossby radius of deformation, which we have looked at. So the main problem that turns out is that for the dry waves there are large observed wave lengths and corresponding wave numbers, corresponding equivalent depths that we get here can be observed, dry waves, so that there is a correspondence between the vertical wavelength and the equivalent depth we compute from the derivations we made here. But for convectively coupled waves where you have the heat source, the equivalent depths that we get are much smaller compared to the wavelength and the corresponding equivalent depths we get from this relation. Okay, so that's something that has to be resolved. We'll see that in a minute. So the troposphere has the heat source. It sends waves up into the lower stratosphere. So the stratosphere equivalent depth is a little bit smaller, 6.1 kilometer. Obviously the lapse rate is positive because of ozone. You know that the temperature gradient reverses. We are just looking at the lower stratosphere where the troposphere communicates strongly with the lower stratosphere. So you are looking again at the equivalent depths and the vertical wavelengths, which are also smaller in the stratosphere, and the gravity wave speeds are the same, and the Rossby radius of deformation are the same, as you remember from the relations. Then dry waves are observed. They do get explained by in terms of the vertical wave lengths and structure and equivalent depths, but the convectively coupled waves still remain a problem in terms of observed parameters, vertical structure and wavelengths and corresponding equivalent depths. Will adding moisture help this problem? So you can do that by changing our vertical equation, which we had 0 before for dry waves. You add a heat source. This should be actually on it's the heating rate, and we are not going to worry about the horizontal movement yet, but you can make the heating oops, I missed that equation, but basically you can make the heating proportional to n squared with this relation alpha n squared. So you make this alpha n squared and move it to the other side, you get this relation. So it looks like the equation we had before, except we have now the parameter alpha, which is the relation between heating and vertical motion, right? So the stability and vertical motion and the heating rate are all related now. So the problem of finding the equivalent depths for convectively coupled equatorial waves to explain their slow movement and the vertical structure and the equivalent depths, we just move from one problem to the other. So here it comes down to estimating alpha, which we will look at a little bit later. So the other key parameter, that key boundary condition that matters for these vertical waves we want to look at is what is the boundary condition at the top? Are the waves just radiating out like from the troposphere into the stratosphere, or is there a rigid lid at the top? So you can put two boundary conditions and derive two solutions, and they look remarkably different, but it's realistic in the sense that in the stratosphere here, for example, you can see the pressure levels, hectopascals, going from the surface to the top of the troposphere and above the troposphere into the stratosphere, the lower stratosphere. We are looking at zonal vertical cross sections of Kelvin wave, zonal and vertical wind vectors, and temperatures constructed by using a vertical structure function corresponding to two different boundary conditions. You look typically at vertical structure function multiplied by the horizontal structure, which is the same for both boundary conditions. So here you have exponential z over 2h cosine mz plus kx. That gives you this solution with tilting structures, upward propagation, upward velocity vectors and downward velocity vectors here, and the opposite phase of the Kelvin wave. So you have Kelvin wave moving eastward, as you would expect, unless there is a Doppler shift, which we are not going to talk about here, which is much more common for Rossby waves. So you have the equatorial Kelvin wave having this structure in the stratosphere, and in the troposphere you have the vertical structure function given by this expression here. As you can see, they are almost same, but not the same. So the imaginary parts are different for the radiation boundary condition, which is appropriate for the troposphere, versus the rigid lid boundary condition. And the vertical motion here is 1 centimeter per second, order 1 centimeter per second. Same here. Horizontal velocity vectors are 2 meters per second, and the temperature contours here 0.2 Kelvin. So much more temperature contrast here than here, which is 0.1 Kelvin. But you can see the wave structure in the zonal vertical direction here. So you have a counterclockwise and clockwise structure of the in the vertical for the Kelvin wave. You remember the horizontal structure with the equatorial maximum in convergence, divergence, and in geopotential height. V is 0, but here we have vertical and zonal velocity, so V is still 0 in the special case that we have set up here, with constant n and background state being stationary and so on. Okay, so that problem, when we plotted these wave number frequency diagram before for the shallow water system, we had used equivalent depths of 8, 12, 25, 50 and 90 meters, and obviously the equivalent depths we get in this table are much larger. So the vertical structure and the equivalent depths corresponding to the vertical wavelengths do not match observations. So that problem has to be explained, which we will do in the podcasts coming up next. Okay, so I didn't go through the mathematical details, and I'm trying to just explain the physics to you, because this is not really a course I meant to go into the detailed wave equations and their derivations, because that is done somewhat or done in much more detail in my tropical dynamics course. A couple of chapters, you can go through them. Once you do those, you obviously have to add background circulation, SST changes, zonal wind shear, meridional wind shear, vertical wind shear, and so on, to see how waves are affected by the changes in the background states. But we are not going to get into that here. I'm just introducing this in the context of the convectively coupled equatorial waves, since those are important for the MJOs and MESOs. Okay, so we'll leave it here.